Ever wonder why some neural networks operate like magic, solving complex problems with ease, while others struggle, even when built the same way? Today, we're diving into a groundbreaking discovery about ResNets, the architectural workhorses behind facial recognition, self-driving cars, and more. Spoiler, it's not just about depth. It's about how they're constructed. Let's start with a fundamental question. Why do deep neural networks sometimes fail? Imagine building a skyscraper with 100 floors. Each floor is a layer in the network, right? But as you go higher, the structure gets wobbly. Traditional feed-forward networks struggle to stabilize because information gets lost or distorted as it travels through layers. It's like passing a message through a chain of people, where each person only hears part of what the last person said. Now here's where ResNets shine. They're like skyscrapers with elevators that skip floors. These residual connections let information jump over layers, avoiding the wobbles. But this new research reveals there's more to it. It's not just about training stability, it's about math. ResNets don't just train better, they think differently. Think of them as a city with multiple highways versus a single road. Feed-forward networks follow one path, but ResNets explore many, adapting to the data's complexity. The study shows that even when training is perfect, ResNets still outperform others. Why? Because their architecture aligns with the hidden patterns in real-world data, like images, speech, or text. How did they test this? They created two types of networks, one with a fixed number of layers like a straight staircase, and another that could vary depth like a ResNet. Both were trained under the same conditions. And guess what? The variable depth networks crush the competition. It's like comparing a rigid bridge to a flexible one. Both get you across, but the flexible one handles storms better. This isn't just about shortcuts. It's about representation. ResNets can capture intricate patterns because their shortcuts let them explore multiple pathways. It's like having a toolbox with different tools for different jobs, rather than one size fits all. Even with perfect training, the gap remains, proving some advantages are baked into the design. So what does this mean for the future? It suggests that next-gen AI models might prioritize variable depth architecture over just stacking layers. The study even shows that ResNets' success isn't a fluke, it's a mathematical inevitability. Next time you hear about ResNets, remember, they're not just deeper, they're smarter. And that's why they're the backbone of modern AI. Thanks for watching and stay curious. But let's dig deeper into the study's methodology. How did researchers ensure their findings were reliable? They added error bars to experiments on the CIFAR 100 dataset. Why? Because it's computationally simpler than their larger ImageNet tests. Error bars are like a margin of error for data. They show how much results might vary due to factors like random choices in training or different test splits. For CIFAR 100, they clearly explained what these bars represent, like model initialization or data sampling, and how they calculated them, probably using standard deviation or a statistical method. They even mentioned if they used 1 sigma, 68% confidence, or 2 sigma, 95% confidence, bars, which matters for interpreting reliability. But for ImageNet, they skipped the error bars. Why? It's just too resource-heavy. Think of it like trying to measure a soccer field with a ruler. Sure, you could do it, but it's way more practical to use a laser measuring tool. ImageNet is so huge that adding error bars would have required massive computational power and time. So they focused on the dataset where they could be thorough, while being honest about the limitations of their bigger experiments. This transparency is a big deal. It shows they're not hiding anything, they're acknowledging where their data might be less precise. And that's how science works, being clear about what you can and can't say. So what does this mean for you? It's a reminder that even in cutting-edge AI research, there's always a balance between precision and practicality. The team prioritized clarity where it mattered most, and that's something we can all appreciate. Next time you hear about a groundbreaking AI study, remember, the best research isn't just about flashy results. It's about showing your work, admitting the limits, and letting others check your math. Thanks for watching. Drop a comment if you'd like to dig deeper into how scientists make sense of messy data.